Hi, welcome to the week 3 tutorial lesson. And for week 3 tutorial lesson, I'm going to make use of the milling slides that can be found in the week 2 tutorial lesson. Okay. Now for week 3, the home-based learning, I hope that you have gone through this right before I go through my slides. Nevertheless, whatever it is from the slides, you need to extract it and put it in your notes. Now, what will happen is that because this is a recording, what I'll do is that next week I will spend perhaps maybe half an hour to 45 minutes to go through review the salient points or the important points that you should mark out on your notes, okay, so that it helps you in your study for the coming quiz. It will also take the opportunity to ask any questions that you have. Now, the slides for the milling theory, right, for the lesson that I'm going to use, it can be downloaded from the Blackboard, and this is the slide that we're using. Okay, so these are the parts that talk about the topics that we will cover and milling machine introduction. Okay, a machine that does milling, okay, is basically a machine that removes material from a prismatic shaped block. Previously, we learned about turning, and turning is the removal of material on cylindrical components or shafts. Okay, so this time around, you have blocks or parts that are prismatic in nature, meaning like blockish shape, like rectangles or squares, and we use the milling process to remove material. Okay, now there are different types of milling machines. Okay, these are mentioned here, but to note, the one that we are focused mainly on is the horizontal milling machine, which is in the next slide, and the vertical milling machine. For the horizontal milling machine, it is important to understand it's important to understand and label all the parts of the milling machine and what they are for. Okay, the overarm for this is a horizontal milling machine, meaning to say that there is the cutter is mounted horizontal, okay, horizontally across. Can you see it's horizontally across? As compared to the vertical milling machine, where the cutter is mounted vertically to the spindle. Okay, but by and large, these machines have a few portions that are similar. Okay, the ones that are different, of course, is the overarm for the overarm and the arbor for the horizontal machine. Okay, and the rest of the other machines are pretty similar in the sense that they have a column, they have a lead screw jack, they have a knee, they have a table, then of course they have the machine vise to hold the workpiece. Okay, again, for the vertical milling machine, all these terms, right, and how you label them and what they are is important, so you need to take note of that. Safety rules pretty much applies. It's pretty much the same as turning. Okay, never stop a machine when taking measurements, right? Oh, sorry, stop the machine when taking the measurements. Yeah, never handle chips with your bare hands. That's very important as well. Do not remove any safety guards. Okay, and ensure that the work and tool are secure and rigid. Okay, are secure and rigid. So these are the important things that you should take note of. Now, milling cutters, how do they look like? But we'll focus more on vertical milling machines because these are the machines that we'll be using in our practical workshop. Okay, for milling cutters, okay, generally vertical milling cutters look like the ones that we have over here where my arrow is, right? And this one over here, wherever they have a circle with a keyway, those are mostly for vertical milling cutters. Those are, sorry, horizontal milling cutters, okay? Because what happens is that the hole here is for you to put the cutter through the arbor, and then there is a slot at the top of the hole, and the slot is a keyway where you can insert the cutter, and when the arbor turns and rotates, the cutter will move along, will rotate along as well. Okay, if not, they will slip in its place. So this is the for the horizontal milling cutter, and then this is for the vertical milling cutter. Okay. Now the ones that we commonly use at the workshop are the solid milling cutters, pretty much like the one that you see over here. And we don't have this in our workshop, or we seldom use this. We use this one here, right? But these are more for turning tools, right? These are for the throwaway inserts. Now, looking at the horizontal milling cutters, these are the few cutters. This is the self-study portion where you need to take note of and study what they look like. Basically, to identify them, what they are, and what they are for. Okay, what they are for, what do they use for, or what shapes are they used to cut. Okay, so there is a convex cutter, okay, pretty much like this one. Then there is a plain slab mill, which is this one. Okay, then there is a single double angle cutter. Then is a side and face staggered cutter. This is a side and face staggered cutter. And this here is a slitting saw. It's a very thin cutter. Okay, now for vertical milling, the most common tools are the end mills, and they look pretty much like that. And if you look at the end mills, they have several spirals. Okay, each spiral is considered a flute. So an end mill which has 4 flutes, right, will have 4 spirals. And this end mill here has got 6 flutes, so it's 6 spirals. This end mill here has 4 flutes, so it has 4 spirals. Okay, and underneath the end mill there are cutting edges, so that you can actually create slots. Okay, mill slots into your workpieces. There are other kinds of cutters where it is not flat and it is ball shaped, and those are called the ball nose end mill. And these cutters are usually used in CNC mills. Most of the time they are used in the CNC mills so that they can create smooth contours. Okay, smooth contours. That's how they use the ball nose cutter. The common tools for vertical milling machine is the end mill. Alright, and these can be found in your notes. So what you can do is you can take these slides and the condensed point form that you find here on the slides, if you find it easier to study, you can make some notes on your handouts. Okay, and this one is for a T-slot cutter, is to cut T-slots onto plates. And these slots are useful so that you can put in the heads, or you can put in the nuts, okay, so that you can mount workpieces or your components onto this table. Now, straddle milling is is a horizontal milling process. Straddle milling is when you have 2 cutters, right, mounted, okay, at a distance, and then you are cutting the component in one pass. Okay, so 2 components you're cutting in one pass. This is called straddle milling. If anything more than 2 cutters is what we call gang milling. You can see over here. So in one pass, this whole profile is cut. So actually, for horizontal milling, the horizontal milling machines is ideal for companies or shop houses that do small batch production, okay, of components. They make use of horizontal milling machines so that in one pass they can machine out a contour, okay, accurately, so that it's easier to so that it reduces the setup time, it reduces the machining time. Okay, so it improves productivity greatly. But most of the time in a typical machine shop, most of the time people would have a vertical milling machine instead, because it is more versatile. Why more versatile? Because you can do drilling operations, you can mount blind slots on a component. So there are things that the gang milling can do that the horizontal milling machine can do that the vertical milling machine cannot do, and then vice versa. Okay. Now these are the common vertical milling processes. Each of these processes you need to identify them, know them, and then remember how to, or memorize the short description of what they are and what they can do. Okay, So these are all the processes. I'll mention briefly why some of these are done. Okay, like countersunk. To do a countersunk means on the top surface here, there is a conical shape that is removed, like a hole, a slot that is removed, conical shape. Because sometimes when you use your screw, you use those flat head screw, and you want the screw head to be flush to the component. So you need to use this countersunking tool to create that cavity, that shape there. Okay. Tapping, of course, as you know, is used to create threads. Chamfers, drilling, counter boring, rimming. Rimming, I mentioned before, is to make accurate sized holes. Okay. Now, the fundamentals of milling process. Okay. In the milling process, be it vertical or horizontal milling machine, milling operation, okay, there are two types. One is peripheral and the other one is phase. It is important to identify the difference between the two. Okay, for peripheral cutting, right, the cutter axis, which is this, imagine where my mouse is, the cutter axis is parallel to the cut surface. Okay, and the peripheral of the cutter is doing the cutting. So this is peripheral cutting. So even on the vertical milling machine or horizontal milling machine, we can still do peripheral cutting. Okay, there will be times where we do peripheral cutting, and then there will be times where we do face milling. Okay, so when you do peripheral cutting, okay, you are using the peripheral of the cutter to do the cutting, and the surface quality is wave-like. So there is you will see wavy patterns, okay, like these lines that go across. Now, those of you who have followed me on the first day of the milling class, you would have noticed that when you do a rough cut, a very fast rough cut, there are rough patterns generated on your surfaces, and they look like straight lines, wavy patterns, and that's because the first week, right, what we did was what I call peripheral cutting. Now, face cutting is different. Face cutting is where you are using the face of the cutter. Okay, so right now the cutter axis is perpendicular to the cut surface, and you are using the underneath of the cutter to remove material, right? And the surface finish has circular cuts. Okay, now apart from apart from peripheral milling and face milling, right? The milling direction actually affects the surface finish. Okay, so there is one convention, or there are two different types of how do you call that, feed direction, but with respect to cutter rotation. We call it upcut. Okay, so the illustration that is shown here is that of a horizontal milling machine, but however it also applies to the vertical milling machine. So you only need to view it from a different perspective. If you are looking at it from a horizontal milling machine, you are looking at it at a front view over here. If you are viewing it from the perspective of a vertical milling machine, then you are looking at it from the plan view. But because over here, when they draw the cutter with the circle and the keyway, this is actually they are using a horizontal milling machine as an illustration to explain what this is, upcut. So upcut happens when the work is fed against the cutter teeth. So the work is going in this direction, and the cutter teeth is coming in, and it is as if the cutter is digging into the workpiece, and not say digging in, it's like going into the workpiece and lifting it up. Okay, lifting it up as if it's trying to pull it out of the vise. Okay, now when this happens, okay, the cutter wears due to initial rubbing. It wears a little bit faster, right? And the surface finish is actually slightly poorer because there are some times where the chips are thrown in front of the cutting zone, and then therefore your surface finish may be poorer. Okay, so there is rubbing. So that is what happens during the upcut, right? Upcut. This milling conditions, this milling is more sometimes preferred in older machines because of backlash. Right? Backlash has no effect on the cutting in this direction. Whereas if you are going for down cut, right, down cut, Down cut is the opposite, right? Where the work is fed with the cutter teeth. So now, as your cutter is rotating this way, and the workpiece is moving in the direction of which the cutter is rotating, the work is fed with the cutter workpiece. When this happens, right, the work tends to be pushed down. Thus, therefore, it actually improves the clamping rigidity. That's one thing. And the chips, right, are thrown away from the cutting zone. So therefore, your surface finish is a lot better. For those of you who followed me during the first week of machining, you'll realize that in one direction, your surface finish is poorer, and in the other direction, surprisingly, your surface finish is better. And if you can recall, that is because you are actually doing a down cut. Okay, you are actually doing the down cut. Okay, that's why your surface finish is better. Okay, so that's what's happening during the practical lesson. Now, the fundamentals of milling process, it is important that you understand these diagrams over here. I would suggest you maybe even screenshot, copy, and paste, physically paste these pictures in your notes, okay, so that when you study, you can recall. I don't suggest you memorize because you could end up memorizing it wrongly, but I suggest what you do is you try and understand the logic behind it, and from there you are able to deduce whether it is an up cut or a down cut, okay. These two diagrams here are especially important. Okay. Now, what are the factors affecting cutting? It's very much similar to turning, right? You have your cutting speed, depth of cut, and feed rate, your workpiece material, your tool material, geometrical profiles, cutter fluids. And but one thing extra is number of teeth actually plays a part, okay, or number of flutes on the cutter. The direction of cut, whether it's up cut or down cut, plays a part in your cutting conditions, your factors affecting the cutting. So these last two portions are extra compared to turning. All right. Now going down, cutting tool characteristics. The softest tool is listed at the top, and the hardest tool is listed at the bottom. It is important to understand this, the flow of this, the sequence from soft to hard. And it's important to understand the different kinds of materials that are being used for the for cutting tool materials. Okay, going down, this is important. Please put a note on your handouts. Right, even for the cutter, they have positive rate angle and they have negative rate angle. So this one over here is a positive rate angle. This diagram picture here shows a positive rate angle. And what happens is that the rake face slopes backwards. Okay, the rake face slopes backwards. There is a higher tendency for the cutting edge to break because it is not supported at all. However, it is at this positive rate angle that the surface finish is better. Okay, however, you need to lower your cutting force. You need to control the cutting power so that your tool do not wear off or your tool do not chip off unnecessarily. Now, cutting negative rate angle is when your rake face slopes forward. Okay, the normal force is acting into the tool body, so it's supported, so your tip of the tool does not chip so easily. Okay, and it is generally used for cutting more brittle materials. We are here again discussing about cutting fluids, and it is exactly identical to the ones in the turning slide. Okay, and it is important enough for me to repeat that the main two important functions of cutting fluid is cooling and lubrication. All right, it's cooling and lubrication. The rest of the other points are the effects of cooling and lubrication. Next, we go into the calculation aspects of milling. Similarly, we need to remember the formula V equals to pi dn over 1000. Okay, and the V here is your cutting speed. Your N is your spindle speed. That means the speed at which the cutter rotates. And the D this time round is not the diameter of your workpiece anymore because your workpiece is a prismatic block. The D here represents the diameter of the cutter. Okay. So that is the formula that you need to memorize and remember. Okay, and then there is feed rate. All right, feed rate, and usually what is given is feet per revolution. Okay, and that is actually feet per tooth multiplied by the number of teeth. So the number of teeth actually affects the feet per revolution. Then when you know your FR, which is a feet per revolution, multiplied by the spindle speed, you get your feet per minute. So ultimately, what we are trying to calculate or make use of is the feet per minute. The machining time is the length of the workpiece that you're machining, alright, divided by your feet per minute. Okay, and that's your machining time. These examples can be found on your home-based learning. Okay, and we're going next into tool holding devices. Now, for tool holding devices, you have your spring collet. This is called a spring collet, alright, and this here is the spring collet, and this is where the tool gets inserted in, and this is a lock nut. As you tighten the lock nut, the spring collet will grip onto the tool and hold the tool. Okay. Now what happens is that yes, now we're going to talk about work holding devices. So how do you hold your workpiece? Commonly, in your tutorial, in your practical lesson, you'll be clamping your workpiece on a hydraulic vise. But there are times where your workpiece becomes too large for a vise. You will then possibly need to mount it on angle plates instead. And this is an angle plate. Angle plates are made of hardened steel that have been ground accurately 90 degrees. Okay, so this is mounted on the table, on your milling table, and it is actually set up. You need to use a dial indicator to set up to ensure that it is parallel to your table, so that when you machine, you can ensure that your workpiece is machined in parallel to the direction in which your table moves. Okay, if not, one end will be thicker than the other end. These are V blocks. V blocks are used for machining of cylindrical shafts or to secure cylindrical shafts. You put your cylindrical shafts over here and then you secure it. Then you have all these clamping devices, clamps, okay, especially when you have very large workpieces. Okay, the common type of clamps that we see, we have a step block, okay, and a clamp. Then there is a U clamp, which is this one over here, and there is this very unique shaped clamp that's called the gooseneck clamp. Okay, so please put a star on your handout. All right, you need to remember this, like what a gooseneck clamp looks like. Alright, these are the different types of clamping techniques and which one is correct and which one is important. And if you understand it a little bit, it's all about clamping in a way where your workpiece is most secure. Okay, machine vices, you have your plain vise, swivel vise, and universal vise. Okay, so it's important, this topic here, to take note of it. A plain vise or a typical vise have got a fixed jaw and a movable jaw, and then they have a handle right together with a lead screw. Okay, so the movable jaw will move and secure your workpiece to tightly before machining. Right? A swivel vise is where the base of the whole entire vise is able to swivel so that you can machine your workpiece in angles. Right? And a universal vise adds an additional angle of movement or angle of rotation, which is along the x-axis. Okay, it rotates about the x-axis. The swivel vise rotates about the y-axis. Okay, so universal vise allows you greater flexibility in mounting your workpiece to create shapes that are otherwise very difficult to position and to machine. Okay. Next, we have jigs and fixtures. It's important to know what's the difference between the two, right? A fixture helps you to guide your workpiece, okay, and to secure it repeatedly before machining or in assembly, right? A jig, however, is usually mounted on your workpiece, or your workpiece is mounted on a jig such that it guides a tool to machine accurately onto a location. Okay, so the jig actually works together and guides your tool, whereas a fixture doesn't guide your tool. A fixture just accurately locates, so that you don't have to do your setup. You reduce your setup time, right? Now, the next devices that we commonly use are parallel bars, and we make use of parallel bars to prop up our workpieces or to position our workpieces such that they are central to the clamping zone, so that it's more secure. Okay, that's why we use parallel bars. Okay. All right. So the key considerations for milling, okay, the take home that we have that you should take note of is that for rough cuts, that means you're removing a lot of materials, you should have a low cutting speed. That means the speed of your cutter should be rotating at a lower speed, right? And then you have a faster feed rate, you have your large depth of cut. Okay, now in your workshop, right, cutting to a depth of cut of 1 mm, 1.5 mm is considered a deep depth of cut. Okay, low cutting speed is like 900 rpm, 800 rpm. That's low cutting speed. Now, if you want to achieve better finish, okay, instructors usually recommend 1200 rpm. But if you want to go up to 1500 rpm, you can, okay, safely do so to get better finish. Then your feed rate has to be lower and your depth of cut has to be small. The depth of cut has to be 0.1 or maybe even 0.2, right? And not more than 0.2. Okay, so 0.1 you have a very good surface finish already. Alright, with that, these are all that I've covered in the milling slides. I know it looks really brief and it's really fast, but what I'll do with you guys next week when we meet again in class is I'll go through with you what's in your handout, and the key important points, we will revisit them again. Okay, like up cut, down cut, I'll revisit them again because I'm sure some of you will be a bit confused by that. We will revisit what is peripheral milling and what is face milling. Okay, and we'll revisit cutting conditions as well. With that, I hope you enjoy your holidays so far, and I'll see you again next week. For my other class, I'll see you for the workshop session this Friday morning. Till then, see you again and have a good evening. Bye bye.